Okay, I accidentally did a bunch of talking to myself without recording, so I got a lot highlighted here. I think this is working now. But I've got the general form here of our transformation of a trigonometric function. So we're just letting trig stand for any of the 6 trigonometric functions, and we have the transformations A, B, C, D, where we've already talked about them in terms of vertical stretch, vertical shrink, horizontal stretch, shrink, shift left, shift right, shift up, shift down. Now we're going to put in a few more words to go along with them. So first, we have the A value is also called amplitude if you're talking about the graph of sine or cosine. If it's not sine or cosine, we just call the vertical stretch factor as we were doing before and we do in previous types of graphs, but it's got a special name, amplitude, for graphs of sine and cosine. Then D, which is the vertical translation, doesn't get a fancy name. It's always been called vertical translation or shift up, shift down. Vertical translation is already its fancy name, I guess. Then we do get a fancy name for our phase shift. So the phase shift of the graph is the quantity C divided by B. So if I have it written as BX minus C, remember that we have to factor out B and make this B times X minus C divided by B, and that's the phase shift. Because B is a multiplicative change, if you want to know the left-right shift, you need to have B factored out. So C itself is not the left-right shift, it is C divided by B, and the fancy name for that left-right shift is phase shift. So the phase shift is left-right. Now, the way that this is stated, because the negative is part of the formula here, if C is a positive, the graph is shifted to the right. So if it's shifted to the right, it is minus C over B, or minus C right here. If C is negative, you're going to see the positive inside the formula because that's the left shift. So just keep in mind that they're using this formula that already has a negative built into it. So they're saying that if it is minus a positive value, you're right shifting, and if it's minus a negative value or has a plus in it, it's left shifting by C over B units. That's the phase shift. We also have a note that horizontal translation also applies to any vertical asymptotes, and we often must manipulate the function to find this value. Yeah, okay. Like we usually factor to manipulate the function. That's an example of manipulation. All right, then we have the period of the graph. So the period is going to depend, it is the distance between repetitive patterns in the graph, and it's going to depend on what kind of function. If you have one of the sine or cosine or their reciprocal functions, cosecant or secant, then it's 2 pi divided by your b value. The b value, as we saw in some of the previous graphs, will condense your horizontal distance, and so that's going to help get you the period. And then if it's tangent or if it's cotangent, their ordinary period is b, so if you have a horizontal stretch, it's going to be pi divided by b. The ordinary period is pi, I meant to say, so it'll be pi divided by b. And finally, the frequency. So the frequency of a function is the reciprocal of its period. So if I know the period, we're just going to flip it. So instead of pi divided by b or 2 pi divided by b, it's b divided by 2 pi for sine, cosine, cosecant, and secant, and for tangent and cotangent, it's b divided by pi. All right. Now, let's take a look at the next one, and I already wrote a lot before I got to restart this video, so I'm going to rewrite it this time here. So I'm considering the function y equals negative 2 cosine of 2x minus pi plus 1. And we want to talk about the amplitude, the period, the x-intercepts, the y-intercepts of the function's graph. Okay, we want to predict these things. So, the amplitude. This one we can do because for this one, we just need the a value. So the amplitude is the absolute value of a. And I already wrote them down, but we can slide down a little bit and just see them before we get started. We can write down what a, b, c, and d are. A is negative 2, b is 2, c is pi. It's not negative pi. Remember, they have the negative as part of the formula. C gets to be pi, and then d is 1. So if amplitude is the absolute value of a, then the amplitude is 2. Okay, then the period this is a cosine function, so it would initially have a period of 2 pi, but we're going to divide it by b and take its absolute value. So the period is 2 pi divided by b, and so in this case it's 2 pi divided by 2, or it's pi. All right. Then we're going to look at the graph of the original function and do some sketch work on that to try to figure out what the x-intercepts and y-intercepts of the new graph are going to be. Now, unfortunately, this graph has a lot going on, and so it's going to be messy to figure out the other two pieces. These two are the nice, friendly pieces because there are formulas for them. Formula for amplitude, formula for period. I can tell you the phase shift. I know that the phase shift of this graph is c over b, so it is pi halves. But that's not what they've asked me for. They've asked me for the x-intercepts and the y-intercept, so now we need to go ahead and find those. So to get to those, let's think about what has been done to this graph. All right, so I'm going to redraw the original cosine function, and I'm going to try to draw a couple different transformations to it. So if I have 1 and negative 1, let me push that up, 1 and negative 1, and then pi halves, pi, 3 pi halves, 2 pi. So I'm just going to label them for the pi's. Same thing on the backwards. We have, negative pi halves, negative pi, and negative 2 pi. I just didn't label negative 3 pi halves. Wasn't going to label that one either until I put my pi in the wrong spot, but there we go. And so the cosine graph starts up at 0 on 0, 1, and it goes through, then it goes negative 1 at pi, and then back up to 1, 0, negative 1, 1, and back to 0. So the cosine, I missed something because I was supposed to go 0 there and 1 here. So ignore that. There we go. Okay, so this is our regular cosine function. I got a lot of things to do to it. So I'm going to try to draw over this graph in some light colors so we can hopefully see all the changes. So the first thing that we want to do to it is something about the period of this graph. So we're going to do that inner horizontal stretch first. So we're doing a horizontal stretch. We've got a 2 factor. So we're going to draw this graph with a period of pi instead of 2 pi. So we've got to get all the way back up to 1 in pi. So that means that I'll be at negative 1 at pi halves, and we're going to hit our zeros right in between. Okay. So let's draw that much narrowed graph. So we'll hit our zeros right in between. And so this would be the graph that has, so I'll label in a second. So this orange one is the graph of just cosine of 2x. Okay, that's only one of the tiny minor changes that we need to make. The next thing that we need to do is phase shift it. So we need to graph cosine of 2x minus pi. Remembering that this is a phase shift of pi halves because that the 2 factors out. This is cosine of 2 times x minus pi halves. So we're going to be shifting this to the right pi halves. And so pi halves are these markers. I might just label them to make it even more clear. So that's pi halves. Okay. So in my brownish color, I need to shift everything that far. So I'm going to go up to here. I'm going to go over each of the ticks that I drew was pi halves. So we're shifting these all over. And keeping, okay, so orange, keeping things in their respective right places. So I will go this. All right, so we've got a lot going on already in this orange graph. I'm going to have to highlight it in a second. That got shifted over here. Okay, and then this got shifted right there. This got shifted right there. And that got shifted right there. So that's orange. Okay, so that has just the, I don't know if we can see that any better. Probably not. That has just the two horizontal pieces. Now we need to get those vertical pieces in. So we're going to flip it and we're going to stretch it vertically. So I'm going to flip it, which means that the peaks become the valleys and so on. So I got to draw below because I don't think I can draw one more graph on that grid. So let me get my pi halves, pi, etc. markers up here. So pi halves, let's start just drawing one side of it. There's a lot going on here. So pi, 3 pi halves, and 2 pi. Okay. We also now have those half markers because this is the pi quarters markers, because when we shrunk our period, we have to go through the pi quarters markers as well. Okay, so in the orange, we have, I'm going to circle my points that I'm going to be flipping right now. Okay, so we're going to be flipping these across to the x-axis. So up 2, so I'm going to have a point up 2, then at pi halves, we're going to be down at -2, at pi, we're going to be up at 2, and then at 3 pi halves, we're going to be down at -2, and at 2 pi, we're going to be up at 2, and we're going to go through 0 on those quarter markers. Okay, approximately. Oops, sorry guys. I need to watch my screen as my computer screen as well. This part of it is now the -2 cosine of 2x minus pi. The last thing I need to do is add the 1 to it. This is the worst part, really, is adding that 1, because when I shift it, I basically move the x-axis down here. I'm no longer symmetric. I have more of the graph above the x-axis than I do below, and so figuring out what those zeros are is going to be challenging. Okay, so I can find the y-intercept nicely, which is one of the things I need. So my y-intercept should be up there at 1, 2, 3. It should be at 0, 3. The x-intercepts are going to cause us some problems still, and I can't find them with this transformation graph that I found because they're not part of the original center line. Right? If I move my x-axis down here, where this is 1, 2, 3, and this is -1, I'm in trouble because I'm not symmetric. That's what I finish off this graph with, is moving that down. So, to find those x-intercepts, which my question asked me for, I'm going to have to do some work. So first of all, the x-intercepts will take the original equation, 2 times the cosine of 2x minus pi plus 1, set it equal to 0. So -2 times the cosine of 2x minus pi equals -1. Divide off the -2, cosine of 2x minus pi equals +1/2. Need to grab a unit circle, and I need to find places where cosine is equal to 1/2. One of those is up here at pi thirds, and the other one is back down here at -pi thirds. So if I set the 2x minus pi, the inside, equal to those two angles, pi thirds, and 2x minus pi equals -pi thirds, we might be able to solve for x. So if I add pi to both sides, common denominator, of course, that's 3 pi plus 1 pi is 4 pi over 3, and common denominator here, Add pi to both sides. 3 pi minus 1 is 2 pi over 3. So x equals 3 minus 1 is 2 pi over 3. And then divide by the 2's. So x equals 2 pi over 3 and x equals pi over 3. Okay, so back to the picture for a second. What we have right here is that this first one is pi thirds. The second one is 2 pi thirds. But because I'm not symmetric, they're not evenly spaced. So 3 pi thirds is pi. That's not going to be one of them. So I have 1 pi third, 2 pi thirds. I don't have 3 pi thirds. Then I do have 4 pi thirds and 5 pi thirds. So for my x-intercepts, my pattern is going to be, I get pi thirds, comma 0. I get 2 pi thirds, comma 0. I get 4 pi thirds, comma 0, and 5 pi thirds, comma 0, etc. I need a pattern for that. I can't just say k pi thirds. I can't even say odd pi thirds because those aren't pi's. So we actually have to separate them and do pi thirds plus, if I, let's see, if I add a whole pi, I get to 4 pi. So pi thirds plus k pi, comma 0, and so that one takes care of these two and things of that form. And then if I want the other ones, I have to do the same thing with 2 pi. So 2 pi thirds plus k pi, comma 0, and then that takes care of the 2 pi thirds, and if I add k pi, that's 3, 2 plus 3 is 5, it takes care of this one. So together, that is my x-intercepts. So this question shows us a little bit of the complexities towards graphing these trays. We can definitely talk about things that we're not used to in terms of graphs, things like amplitude, period, phase shift. Those things we can talk about relatively quickly, but the things that we're used to talking about graphs in terms of x-intercepts, those take a lot more work to talk about. Let's take a look at the actual graph on Desmos and see how good of a job we did here. Cross your fingers. Let's see how this worked. So I'm going to start with the base graph, graphing y equals cosine of x. Let me change my zoom right here. There we go. So I'm seeing a full period, at least on this side. The first thing we did was shrink the period. We have a horizontal shrink of a factor of 2 there. So now instead of it replicating every 2 pi, now it's replicating every pi. Then we had our phase shift. So we have that minus pi. And so that was our orange-ish graph that we had here. We have those tops up there at, it looks like pi halves. Let's see if we did a good job. Tops at pi halves, fantastic, feeling good about that so far. Then we come back over here and we do the reflection, and so one at a time, that's just the reflection, right? You've taken the tops down to bottoms, and then we also make them twice as tall. So there we go. And then the final piece is that up one where it boosts it, and so the line of symmetry is no longer going through the middle, and we have those weird x-intercepts. Again, if your graph is not giving you exact values right here, that's probably because you don't have a step in increments of pi. So just put in a step in increments of pi. Like my step is pi halves, and it's giving me lovely pi interval points right here. So I can see that the x-intercepts are indeed multiples of 3 pi halves. Sorry, I can't talk. Multiples of pi thirds and 2 pi thirds. So 4 pi thirds, 5 pi thirds, 7 pi thirds, 8 pi thirds, and so on. Just like we were able to find by hand.